Okay, thanks everyone for coming. So it's my pleasure to introduce Sebastian Rechberger from the TU Graz in Austria. Sebastian's been working with Melissa and I for about the last year on a new signature algorithm, and he's on his way to CCS to present the results next week, and so he's going to give us the talk here today. So welcome, Sebastian.
Thank you. I'd like to thank Greg for inviting me to stay here a few days at Microsoft Research. Yeah, so we're going to talk about signature scheme today, which is built solely from symmetric-key primitives. This is, besides Melissa and Greg, also joint work with Stephen Goldfeder from Princeton, Claudio Orlandi from Aarhus University in Denmark, and Christian and David from TU Graz, and Daniel Slamanig from the Austrian Institute of Technology. So maybe a short overview about digital signatures. You usually have a signer with a public and a private key who can sign documents using the private key, and then a verifier verifies it using the public key and checks if the signature is valid. It's used in many protocols today, from certificate authorities in TLS to e-government use cases where a person can identify itself, and it has many other applications. But most of the RSA and discrete logarithm-based signature schemes become insecure in a world where we consider a quantum adversary. This is due to a Shor algorithm from 1994. New signature schemes have been built based on new structured hardness assumptions, for example, from lattices, from assumptions from coding theory or supersingular isogenies, and other new assumptions. And there are also some signature schemes which are built from symmetric primitives. The most prominent example would be Sphinx, which is a hash-based signature scheme. Yeah, so we asked the questions if there are other alternative ways to build a signature scheme, also only relying on symmetric primitives. And we base our signature scheme on two recent progresses from recent years. One is based on recent work on symmetric key primitives that only require very few multiplications, or in our context, few AND gates. And the other recent progress we use here is that zero knowledge proofs for general circuits have become practical. And we build our signature scheme on these two advances. We'll need one-third a primitive, which are called Sigma protocols. These are interactive protocols where a prover wants to convince a verifier that he knows something, and they have this three-move form where first the prover commits to some randomness, then the verifier sends a challenge to the prover, and based on the challenge, the prover sends some response, and the verifier can then verify the statement by using the response and the commitment to the randomness. They are also known as honest verifier zero knowledge proofs, and can be very useful, and they allow to build also non-interactive versions of the zero knowledge proofs via a well-known technique by Fiat-Shamir, which is already very old. On the one hand, this allows to get a non-interactive proof, but also allows to get a signature scheme from any Signa protocol. In our case, we look at a statement which is built from a one-way function, and we have use a secret key and input on one-way function, and the public key will contain the image of the one-way function. And then we use a Sigma protocol to prove the knowledge of the input under that function, and use the Fiat-Shamir transform to turn that into a signature scheme. Yeah, so now let's look at an example of such a Sigma protocol. So ZKBoo is a Sigma protocol for arithmetic circuits. So any function you can solely represent by field operations plus in the multiplication, and it is based on a paradigm by Ishai et al., which is called MPC in the head, where you perform an MPC computation on the prover side, and then you'll open some of the computations. And the basic idea is the following: you have some circuit, and then you share this circuit into three parts. The idea here is that if you have these three parts, you can always reveal two of them without revealing any information on the secret input. Then one commits to the evaluation of this shared circuit and can open two of the evaluations to the verifier, and the verifier can then check the consistency of the evaluation. And here, every time we have to, if there's a multiplication in the circuit, we have to take into account various inputs from other branches. And so the efficiency of this protocol heavily relies on the number of multiplications in the circuit. Right. So as a first contribution, we've improved ZKBoo to a variant that we call ZKB++. And on the one hand, we have carefully identified some values that we do not need to be transmitted to obtain the Sigma protocol, and also perform some optimizations where we require the random oracle model, which we'll have to use anyway because we use the Fiat-Shamir transform, and there we have to use random oracles. Then we've also removed many checks that were in the original protocol, but which are rendered obsolete by our optimizations. And so we end up with, we can reduce the size of the proofs by around half the size, but don't pay any extra computational cost. So I'm not going too much into the details on what we did for the optimizations, but some of them were more easy observations where we've just defined very carefully how we perform the initial secret sharing, and use an PNG that we use anyway. Where we have to publish the seeds, so we don't have to include the inputs in the proofs, and can remove some parts of the proofs, for example. But then we also have some optimizations where we require the random oracle model, and here in particular that we build an signature scheme out of it. And whenever you perform this Fiat-Shamir transform, you'll have to hash the commitments that were sent in the first phase. And so since these commitments that we hash here also contain commitments already, then we view this challenge that is computed by the random oracle as a commitment to commitments, and can remove some of the commitments that we would have to send otherwise. Yeah, we do something similar to the output shares that we did to the input shares, and can remove those shares because we can recompute everything, and can then check the computation was done correctly. We are just one output share.
Now this sounds like you're paying computational cost because you say
it sounds like that. But on the other hand, the original protocol had checks for after every multiplication that that the computation was correct. But we use again here some properties of the commitments that they're binding. So unless you've computed that correctly, you so we remove all these checks and use the binding of the commitment to check the computation. And this saves a lot of checks in between. Then we also have another optimization based on the random oracle model, where in the commitments during the protocol, if you consider hash-based commitments, you'd always add an extra some extra bits of randomness. But since our first commitment is the seed that we use for the PNG, which is derived randomly in the beginning, we used the random oracle so that we can reuse that as randomness in the commitment. Saving again some bits and bytes that we don't have to include in the proofs. And then this is one of the other major optimizations that saves a lot of data. So if when you verify the circuit, you'll have to recompute two of those branches, and we observed that you can recompute one of them simply with what you have in the proof that you need to recompute anyway, and then again use the binding of the commitment that you can only recompute that correctly if you so that we use here that the commitment only verifies if the view was computed correctly, and so that we don't need to start a view. Right. Okay. Right. Mentioned that we built the signatures from one-way functions here. So our first construction, which we called fish in the paper, which is now picnic FS, we use this ZKB++ and an OVF as a one-way function to build the signature scheme. And here we use the Fiat-Shamir transform. And this gives us a provably secure signature scheme in the random oracle model. But then if you consider the Fiat-Shamir transform signature scheme in a random oracle where the quantum adversary has where the random oracle is quantum accessible, you'll have some problems. The original, so the Fiat-Shamir proofs requires rewinding, and it's not clear how to translate that into the QROM setting. There's some recent work by Unruh which defined some conditions where you can transfer it, but our construction doesn't meet those conditions. But fortunately, there is a transform that is called Unruh's transform, which helps to use a similar technique to get the signature scheme out of Sigma protocols. And what this Unruh transformation does, it adds an extra random permutation, and you compute responses for some of the possible challenges, and then you apply the random permutation and produce the challenge based on the output of the permutation. And then using this transformation, we get a signature scheme which uses again ZKB++ and a one-way function to build a provably secure digital signature scheme in the QROM. In the paper, this was called Picnic, and which we now call Picnic UR for Unruh. Right. So The Unruh transformation incurs some overhead, since you'll have to serialize more data, including some of the permutations of the responses. So it gets more expensive, but we could get it down to a factor of 1.6 compared to the original Fiat-Shamir transform signature scheme. Right. So okay, this is all right, but we need to select some one-way function which works well with Setkeboo, so has a very small number of multiplications. So if you look at one of a signature that is produced from with this technique, you'll have a factor that is influenced by the number of multiplications and the underlying ring or the underlying field size. So you'll have some constants, C1 and C2 and C3 that only depend on the security level you want to achieve, which are influenced by the size of the commitments, size of the seeds for the pseudo-random number generator, and so on. But then you have one factor that is solely composed of the multiplication count of the circuit. So you're interested in finding a circuit for a one-way function with a very small number of multiplications, but also where it's not only a small number of multiplication, but where also the product of the ring size and the number of multiplications is small. Right. So we've looked into some of the one-way functions that one can build from block ciphers and hash functions, so we've looked at AES, SHA-2, SHA-3, and all of them have a rather high number of multiplications, where you end up with where the product of the field size and the number of multiplications is over 4,000 or 5,000, or for the hash functions over 20,000. But there are some new proposals for lightweight primitives, which all allow to reduce this product. And the best possible fit in our case was LowMC, where we can get to, even for 128-bit classical security level, we can get this product below 1,000. But this is kind of very abstract. So if you look at then final signature size numbers, you can see that if you look at numbers for LowMC, you'll get signature sizes which are around 100 kilobytes, and for AES-based or something like that, you'll get 300 kilobytes, or for SHA, something that is larger than 1 megabyte. So let's take a short look into LowMC. So this is it's a lightweight block cipher design, which allows to select the parameters based on many different metrics. So one can parameterize in a way that you, for example, minimize the number of n's that have to be computed per input bit, or also you can minimize the end depth. And so there are some example of instances where each of them minimizes one of the three matrices. For us here, since this is then a binary circuit, the number of n's is the most important thing for optimizing the signature sizes. Also, one nice thing about LowMC is that it can be parameterized in a way that you can select a very small data complexity, which means that in our case, an adversary only sees one plaintext ciphertext pair. But this is a very unusual setting for a block cipher. But for LowMC, you have ways to reduce the number of rounds if you know that this smaller data complexity is enough. So we've looked into different instances for LowMC at the 256 and 28-bit classically security levels, and you'll always get pictures like that, where if you increase the number of ends and thus increase the number of the signature size, you'll get faster signing and verification algorithms. But pay that in the signature size. And if you try to reduce the signature size and reduce the number of ends, the linear layer of LowMC becomes very expensive, and the runtimes explode. But you'll get smaller and smaller signatures. So we've selected instances that at some trade-off between a runtime and signature size. So when we started to implement the signature schemes, we already got some good runtime numbers with around 30 milliseconds for signing, and verification was a lot smaller, faster with around 17 or 16 milliseconds. But since then, we were able to optimize these algorithms a lot more. And what we've submitted now to NIST, to the NIST post-quantum competition, achieves a lot faster signing and verification times, and almost reduced it by half here. We've also compared it to some other recent proposals, in particular to Sphinx, which is one of the other signature schemes which only relies on symmetric primitives, and we've come closer to their signing times, but we can't beat their verification. They also achieve smaller signatures, but pay the price in this secret key and public key size. And then you can look into signature schemes which are based on structured hardness assumptions. And there it is the picture a lot. You find signature schemes which are good at one of all the data points, but not at all of them. So you'll either have large secret keys or public keys, but small signatures, or larger signatures, but smaller keys. But at least in those cases, the runtime for signing and verifying is very good. But for these lattice schemes, for example, the signature generation algorithms are very slow. At the first look, our signature sizes look kind of bad, with around 129 kilobytes or 200 kilobytes for the Unruh transformed version. But if you look at the security level, which in the NIST competition is level 1, which asks for a 64-bit post-quantum signature schemes, we can get that down to around 30 kilobytes for the Fiat-Shamir transformed version, or 52 kilobytes for the Unruh transformed version. And also the signing times go down a lot to around 2 milliseconds, which isn't a lot. Right. And some of these improvements were done by one of our students, Angela Promitzer, who worked on improving LowMC and the LowMC implementation. So I'll present you the LowMC encryption, how this looks like. It has a very nice structure where you start with, you'll add an initial round key to the plain text, and then you'll apply the same round sometimes, where you first apply an S-box layer, which doesn't operate on the full state, but just parts of it. Then you'll add a linear layer where you multiply the state with some matrix, and then you at a round constant and a round key, which is, yeah. So in our case, the important bits are the S box. It's the only place where we have ends. And the other important bits are the linear layer, which is composed of the matrix multiplication of the state with the matrix, and where we compute the round key, which are, so if you reduce the number of S boxes, you'll increase the number of rounds, so you have more matrix multiplications, which then become expensive. One of the problems that we face in the signature scheme is that the input, as the secret key, is shared on every freshly shared on every execution. So you can't pre-compute the round keys, for example, which would be an obvious optimization. If you'd use it as a block cipher, you'd recompute the round keys and would get rid of one matrix multiplication that you have to do on every encryption. But we can't do that here. So we are looking into some optimization techniques which we can perform without involving the secret key. So this is a typical run of one of the LowMC rounds. You'll start with a S with the state, then apply the S box on some part of it. Then you'll have the multiplication with with one of the matrices, then you add the round constant and the round key. And so what we're trying to do here is this part of the state that is not affected by the S box. Some of those, some part of the round key and some part of the constant only affects this part which is not affected by the S box. So we want to move everything that doesn't touch the bits interesting for the S box before we start all the rounds. So we move these matrix multiplications up as far as we can, and then at some point we have to split them in some part that affects what we call the nonlinear part, which is the part affected by the S box, and which only affects the linear part, which we can move up. And so we repeat that until all matrix operations that only affect the linear part are at the beginning of the loop. So we can remove the matrix multiplication of the key with the key matrix with the secret key from each round, and replace it with one matrix multiplication in the beginning with some pre-computed matrix. And then we only have to perform one matrix multiplication in the beginning using the secret key, and can apply that to the state directly before the first round. So this is for the linear part, and for the nonlinear part we can do something very similar, where we then obtain for each round similarly looking matrix. And this matrix is a lot smaller than the original matrices. And we can combine all those matrices into one larger one, and perform this computation also in the beginning, and then split up the output of that matrix multiplication into the bits that affect each level, each round of the encryption. So moving those matrices around leads to a quite significant performance increase of around 30%. Which so the blue lines are in the original version without the optimization, and the green routes are then if you use the optimized encryption algorithm. And we can observe similar figures on other platforms. For example, this was it has the same performance gains on ARM. Right. Okay. So yeah, let me end with the conclusion here. So it's so we've on one hand presented ZKB++, which is an improved zero knowledge proofs for arithmetic circuits, which only is half where the proofs are only half the size than ZKB. We were also able to reduce the overhead from the Unruh transform and presented two new signature schemes in the ROM and QROM. Right. The first part of the optimizations also has, of course, other applications in anywhere you want to have, for example, a non-interactive zero-knowledge proof for some circuit in a post-quantum setting. Right. Yeah, we've submitted those two signature schemes to the NIST post-quantum competition, but there's also a lot of future work that can be done in the area. So the search for symmetric primitives with a small number of multiplications is quite a new one. So one might think there might be another primitive other than LowMC with maybe even less multiplications. It would also one other thing that would lead directly to further optimizations in our signature scheme would be a more aggressive parameter set based on some analysis around the case where you only see one or two plain text ciphertext pairs. Since if this case is better understood and we could reduce the number of rounds here that LowMC needs, then we'll get an automatically faster signature scheme and smaller signatures. Right, and then one also open topic is, of course, some side channel analysis of the signature scheme, which is basically on one hand on LowMC and if there are any side channel issues which would then maybe leak the secret key, for example. Right. Yeah, thank you for your attention and if you have any questions.
Are there any questions? Okay, let's thank him again.
Thank you.